As you guys know, the homework is due today, and next lecture will be a midterm exam. So please do show up. All right. Questions or comments before we start today's lecture? Okay, so let's jump back into where we left off last lecture. Last lecture we were looking at settling time of simple systems, and in particular we looked at the settling time of a system with a pole and zero. And we found that the output step response is basically the input multiplied by the ideal gain that we're calling C here, times a factor which disappears over time exponentially, but nevertheless you have to wait for it to disappear, and depending on what resolution you want, you have to wait longer and longer. So this is kind of an error term. This is a dynamic error term. And for the amplifier that we looked at last lecture, draw that real quick. Basically our standard amplifier that we've seen many times, single-ended version, but of course this also applies to a differential version. This is CL, this is CF, this is CS, and we apply our step function at this point. So this is V step. And we found that the location of the pole is minus F GM over CL effective, the effective load, and the location of the zero is plus GM over CF. And we gave some pretty good arguments for why the pole and zero look like this, why it makes sense intuitively. And also we made the observation that actually, because the pole and zero have opposite signs, right, these are all positive quantities, if the pole and zero were exactly equal to each other, this term would go to zero, and we would have effectively infinite step response. Okay? And the reason that we don't do that in practice is, imagine that P over Z is not exactly equal to 1, but let's say 1 plus epsilon. Right? If I substitute that into this equation, I get that the step response as a function of time is now multiplied by, so this would be, the 1 would cancel out, and I would just have epsilon e to the minus t over tau. Okay? The idea being that you still, if you want to settle, let's say within some percent, let's say you want to settle within 0.1%, and if this epsilon is bigger than 0.1%, then you still have to wait, right, several time constants until you get rid of this error term, right? And the reality is that if you look at these two equations, it requires matching effectively ratios of capacitances within this tolerance. So if you're shooting for 0.1%, forget it, it's not going to happen, right? It's going to be very tough to get that good of capacitor matching. All right, well then let's look at some more practical cases. Before I start that, any questions? Yes, Debo.
Last class we made the argument that the pole intuitively should look like this because GM over CL effective gives a open loop pole, and then it increases because of feedback.
That's right.
Shouldn't it increase by the loop gain? F is just the feedback factor.
Yeah, in fact if you look at the equation, we're going to look at that stability calculation compensation in a moment, so we'll come back to that question. Okay. Any other questions? All right, so what are some practical cases? So practically, you either have a situation where the zero is at a much higher frequency, and as we'll see, effectively, zero is not there. In fact, if I look back at this equation, if the zero is very large relative to this pole, this term goes away, and it just looks like a step response of a single pole, dominant pole system. Okay? The other case is when P over Z is basically on the order of 1. So you can't really neglect the effect of the pole. And we'll see that, you know, in this case, we definitely cannot neglect 0 in the transfer characteristic. So let me actually switch to the slide here. And maybe a little bit hard to read, but if you have it printed out, you can look. So this is the case where P over Z is very much less than 1. And as an example, let's say you have an amplifier with a gain of 4. Let's say your feedback capacitance and your parasitic gate capacitance are about a picofarad. Then your sampling capacitor needs to be the gain times larger than CF, so it's 4 picofarads. And finally, we're driving a 5 picofarad load. And let's say our specifications are to achieve 10 nanosecond settling time with a resolution of 10 to the minus 3, right? So 0.1%. If you look at this equation, then it's very simple to define the error as a function of time. The error as a function of time is the final value, v as t approaches infinity, minus the value at some time ts. This is how long we've waited. And then we normalize it by the final value. And so if I do that, you can see that the error is just this exponential term in the case that P over Z is much less than 1. And so to achieve a certain resolution, I have to wait log of the resolution time, right? If I solve this equation, T is minus TS, T settling time, this should be TS, is minus tau times log of epsilon, right? And that's actually very fortunate, right? Because the log function kind of grows very slow. So if you need more and more resolution, you only have to wait a few more time constants. If you compare this, let's say, with a linear settling time, right? Let's say that settling time were a ramp function, and you wanted to get 10 times more resolution. How much longer would you have to wait? Obviously 10 times as long, right? But over here, if you look at the numbers, if I want to go from 10 to the minus 3 to 10 to the minus 4, I only have to wait a couple more time constants, from 7 to roughly 9. So that's actually very nice. It means that you know, this initial 4 or 5 time constants is really necessary in precision circuits to get to the 1% level, but then after that, just a few more time constants gives you a lot more precision if you need it. Okay? And in this particular example, going back to this example, calculate your F factor. Remember, F is not 1 over C. Calculate your effective load capacitance. Then you check P over Z, which is F times the ratio of CF over CL effective. In this case, it's 0.03, which clearly is much less than 1, and so we have no trouble neglecting that 0. And time constant for the circuit is about 1.5 nanoseconds, and to get, you know, and then basically to get 10 to the minus 3, we have to wait about 7 time constants, right? So in other words, 7 times this is equal to 10, which is our target. And then finally, once you know the settling time, you can actually calculate what GM you need in order to achieve that settling time. So this goes back to lecture 2 or 3 when we look at amplifier design. And there's just one little missing piece there where we said the settling time is related to tau by several, you know, factors of tau. And so here it is. So pretty simple. Okay. Any questions about this example? All right, so the next example we're going to look at is when P over Z is not negligible. And you might think that's usually not the case, right? If you design an amplifier, usually the 0 is much larger than the pole, okay? And in fact, if you look at this example, you can see that it looks like we've cooked up an example, right? Who thinks this example is cooked up, if you can read the slide? So I'm saying I want a gain of 0.25. And I've chosen some component values, and I compare P over Z at the very end here, and you can see that P over Z is about half. Anybody think this is cooked up? Okay, I see a lot of new faces today. Must be midterm time. All right. So those new faces, remember, 5% of your grade. Good time to volunteer. Okay. Well, is it really realistic to say you need a gain of 1/4? I mean, why use an amplifier if you need a gain of 1/4? Anybody? It's realistic? Actually, it turns out there are situations where you do need an amplifier with a gain of 1/4. And a good example of that is if you're building a filter. In a filter, you have lots of integrators. And so these integrators are integrating charge, right? And their voltages are getting larger and larger. And you get into situations where internal voltage swings on your filter could get large enough so that you actually saturate out. You hit the power supply rail. So you have internal stages in your filter that scale the voltage signals. Of course, you'd prefer not to do that, but unfortunately you have to do it. And if you want to scale with precision, right, then you're going to need an amplifier. And so then maybe you could come back and say that this is actually pretty realistic. There are situations where this may come into play. In this particular example, again, we calculate the error, same deal as before, and instead of getting just this exponential term, we also have this extra factor here. And if we now solve for the settling time, basically, we get this equation, which is has this extra term in it, which is related to the ratio of P over Z. And so running the numbers here, you can see that because P over Z is a factor of 1/2, if I plug that into here, it's going to make a big difference. It's actually going to change the settling time. If you neglected the effect of the zero, you would actually end up designing an amplifier that were too slow. So we have to speed up the amplifier a little bit to compensate for that zero. But it's not very difficult to take that into account. Okay, questions? All right. So let me now talk about amplifier settling in kind of a generic way. And this is hopefully a review for most of you. Let's say I have an amplifier that has an open loop response with some DC gain, and let's say that it just has one single dominant pole. Okay. Now we all know very well that the unity gain frequency, let's call that unity of the amplifier, omega UA, is simply given by, so I'm going to assume that close to unity gain, this term dominates, so this will become S over omega P1, where S is equal to omega UA. And so then I can solve for omega UA is A naught times omega P1, roughly. Okay. So pretty simple, right? I have an amplifier, it has a dominant pole, and roughly then its unity gain frequency is the pole times its DC value of gain. Okay? And if I'm interested in midband frequencies, then the gain, when this term is bigger than 1, is simply A naught omega P1 over S, and we just found that A naught omega P1 is just omega UA. So here's a nice approximation that if I'm interested in the midband gain, it's just the ratio of the unity gain frequency of the amplifier divided by the frequency of operation. If I'm operating at half the unity gain frequency, I only have a gain of 2, right? No matter what A naught is. A naught might be 10 to the 9, right? But if I operate at high enough frequency, that gain runs away pretty quickly. Okay, and then what we're going to do, of course, is put this in a feedback loop. And So let's assume for simplicity that our feedback loop has a frequency-independent feedback factor, beta, and this is our input and this is our output. And we know, of course, that the closed loop gain is the open loop gain divided by 1 plus the loop gain. Okay? And if I now substitute for A of S in midband frequencies, that's omega UA over S, 1 plus beta omega UA over S. So this is midband. And let me simplify this a little bit. I can write this as 1 over beta, the ideal gain, divided by 1 plus S over beta omega UA. And so the 3 dB frequency of the closed loop amplifier is beta times omega UA. And of course, this is the basic gain bandwidth trade-off that we're familiar with. Okay. Now, Dibble, does that answer your earlier question? Good. So we can see that when we close the loop, the bandwidth that we achieve is the basically unity gain frequency of the amplifier open loop factored by beta, right? So in the previous example, omega UA was GM over CL effective, and beta we called F. Okay, good. Okay, so what about non-dominant poles? So let's say we have a multi-pole zero system. In other words, we have, let's say, a bunch of zeros, and let's say we have a bunch of poles. Okay? But, of course, we know that this system won't work unless it has a dominant pole, right? If we take this amplifier with all these poles and zeros and put it in a feedback loop, it's going to oscillate, right? Because there'll be more than 180 degrees phase shift at unity gain frequency. So, in other words, this system will only work if omega P1 is much greater than omega Pj, and also the same applies to omega, let's say, Zj. Well, let's call this K, because that's for all K. And if I draw a picture of this, just a pictorial view, is I have one pole, let's say here, on an expanded scale. Then I have a bunch of poles at high frequency and a bunch of zeros at very high frequency. And so if I'm somewhere over here, let's say, this is about 45 degrees, so that corresponds to roughly the 3 dB frequency, then even at this point, the effect of these poles is pretty minor, right? Why is it that I can claim that? Anybody? Based on this graph, right? So these are my non-dominant poles. These are my zeros. And I'm assuming all zeros are sufficiently high frequency that P over Z is basically much less than 1. Okay? So the claim is that these really don't matter. And of course you can work out the equations and see that they don't matter. But what's a nice intuitive way, just graphical way of understanding that? Okay. Yeah, I mean,
the angle is about 90 degrees, so
yeah, very good, right? What we care about is phase, right? So as we go up higher and higher in frequencies, these poles contribute phase, right? So if I go all the way up to here, this is my j omega axis, then now you can see that, aha, these poles are contributing about 45 degrees. But over here, they're contributing very little degrees, right? About half a degree, 1 degree, right? Same with the zeros. They're contributing very little. Because the phase of A of S is basically the sum of the phase of the zeros measured relative to the j omega axis minus the sum of the phase of the poles relative to the j omega axis, right? So this is the angle relative to the j omega axis. So clearly, I can, intuitively, it seems clear that I could, instead of dealing with all these poles and zeros, I could just say it looks like there's an effective pole here. So we call this the effective pole. That has an angle, which is the sum of all these angles, and has a magnitude, which is a product of all these magnitudes, right? And in fact, I can subtract out the angle of the zeros, right? Because the zeros are giving me positive angle, poles are giving me negative angle, so I can in fact subtract out the effect of these poles and zeros, and intuitively it seems clear that I can define an effective value of a pole. Yes, question?
I don't understand how we choose a point in the j omega axis to represent a phase. Why we choose?
So this is just the frequency I'm operating at, right? So this is DC here, right? And at this frequency I'm operating at, let's say, the frequency of the first pole. Over here I'm operating at a frequency equal to the frequency of roughly these poles. Okay? Now, if you don't like pictures, we can do it with math. So let's do it mathematically and show that this is in fact a reasonable picture. So what I'm going to do is start out with the poles. I'm going to just take the non-dominant poles and just multiply this thing out, right? And assume that I'm at a frequency where S over omega pk is much less than 1. So if I multiply these out, I get 1 over S over omega p2 plus S over omega p3 plus S over omega p4. And all the other terms are going to be much smaller, right? Because I have S squared terms, they're even smaller, S cubed terms. They're all too small to worry about, okay? Don't sweat the details. So that means that it looks like I have just one pole, which is basically looks like the parallel combination of all the poles, and that's the effect, the net effect of all those poles on my system. So if you had a bunch of non-dominant poles, let's say you had 10 poles at 10 times higher frequency than you care about, well, they all will contribute an equivalent pole at the frequency you care about. So that would contribute 45 degrees. So if I had 2 poles, right, the effect of equal magnitude, their net effect would be roughly half that frequency, right? And so on and so forth. Well, I can, now let me treat the zeros. So these are the poles. The zeros of the transfer function, let's call this, I've been using bad notation. Let me call this omega z1. I guess I've been calling them z. I'd be consistent. z1, z2, zm. And the idea is that, of course, I can do the same thing if all the poles are small. Whoops. Sorry, if all the zeros are much larger than the frequency that I care about. And so I can write this also as 1 plus s sum of 1 over zk, k equals 1 to, let's say I have m zeros. And again, if the combined zero is still at a much higher frequency than the frequency that I care about, then this is like 1 plus delta, which I can write as 1 over 1 minus delta, right? And so this looks like 1 minus s sum of zk. And then if you now look at this equation here and this equation here, so I combine them, so my total transfer function now is going to be 1 plus s over the dominant pole, and then I have the effect of 1 plus s over, let's say, omega effective 1, and 1 minus s over omega effective 2. Where this is, I'm going to call this omega effective 2. Okay? And then I, again, these two terms are small, so I can combine them, and at the end of the day, it looks like I just have one extra pole. Okay? And that kind of justifies the graphical picture that I drew earlier. Okay, questions?
Yeah, excuse me. Is it possible that the second terms kind of cancel out the first omega p? I mean.
Yeah, that's what we found when pole zeros canceled, right?
Okay.
If they're about the same magnitude, they cancel each other out, right? And on this picture again, well, here's the picture. If I have a pole here and a zero exactly at the same location, they contribute the same angle, right? And they contribute the same magnitude, and so they do cancel each other out. Okay? All right, so all I wanted to do here was justify the fact that oftentimes we just pretend like we have one non-dominant pole, and we do all our compensation in terms of that one non-dominant pole, whereas in fact you know that there are hundreds of poles and zeros in your system. But if your non-dominant pole, if there's one non-dominant pole that happens to be at a much lower frequency than all the others, then you're very well justified in neglecting all the others and just considering the effect of the first non-dominant pole, right? And that's certainly the case with the amplifier that you guys looked at for your homework, right? There you have one non-dominant pole, and then all the other poles and zeros are very much higher frequencies, on the order of fractions of omega t of the device. And so if you're designing an amplifier feedback system, you only have to consider the effects of the first non-dominant pole. Dominant pole, of course, is by design set by your load capacitance in the folded cascode amplifier. Okay, so now let's look at frequencies much higher than the dominant pole. So frequencies higher than dominant pole. In which case, I know from our previous discussion that this is going to be the contribution of the dominant pole, right? We neglect the term 1. And then we're going to get a contribution from this equivalent pole, right? And so I could write this as A naught omega P1 over S 1 plus F omega Q. And it looks like that first pole is just a DC pole, right? It's such a low frequency compared to what we're looking at that its contribution just looks like an integrator. We're getting a full 90 degrees phase shift from that pole. This, of course, I could write as omega UA, just like I did before. And so I simplify things a little bit here. And so now what I'm interested in doing is finding the frequency where my loop gain is equal to 1, which is beta times A of S. And so I get beta omega UA divided by S 1 plus S over omega Q. I want to set that equal to 1, and at that frequency S is equal to, let's say, omega T. J omega T. So if I substitute, I get beta omega UA. Here I get omega T. Here I get 1 plus omega T over omega equivalent squared square root is equal to 1. And so now I can solve. So now I have an equation where the only unknown is omega t. Okay, I won't bother solving this equation. It's simple quadratic. But you can see now that once you have the equivalent pole frequency, the open loop unity gain frequency, and beta, you can solve for omega t. Okay, and just as a check that I haven't made an error, let's plug in the case that we analyzed before. The case we analyzed before was when there was no second pole. That means the equivalent pole is at a frequency much larger than what we care about. So if that's the case, this term is 0, and the equation breaks down to beta omega u is equal to omega t. And that's what we found before. Okay? So now the question arises on how do you choose the location of omega equivalent? Because that might be under your control. By properly biasing your amplifier, you can move this pole around, or if you're doing some kind of pole splitting, how high up does this second pole need to go? And to answer that question, of course, we check our phase margin. So the phase of our loop gain is going to be 90 degrees from our first pole, right? Again, it's a dominant pole, so maybe it's 89 degrees, but who cares? For all practical purposes, 90 degrees. And then the effect of the second pole, so if I look at this equation, this is the 90 degree term, and then this is the effect of the second pole, is just going to be inverse tangent of omega over omega q, equivalent pole. So then how you choose this pole comes down to, and this is a, let's evaluate this at the unity gain frequency. So how I choose this pole depends on how much phase I want it to contribute. Okay? And so I can turn this equation around. I can say this is equal to my phase margin. Actually, my phase margin is how far away I am from minus 180 degrees or plus 180 degrees, the same thing. Because at that point I know I can oscillate, and I can solve this equation. I can say that that's phase margin 90 degrees, let's say, minus phase margin, or this very simple result that, sorry? Oh, yeah, thank you. Okay, thanks. So the simple equation is that basically, depending on how much phase margin you want, you have to choose the unity gain frequency to be tangent of 90 minus the phase margin higher than the equivalent pole that you have. Okay? So, of course, a very simple case occurs when I have 45 degrees phase margin, because tangent of 45 is just 1, and that corresponds to choosing unity gain frequency equal to the frequency of your equivalent non-dominant pole, right? Usually, though, 90 degrees, 45 degrees of phase margin is too aggressive. You're going to get quite a bit of ringing. If you look over process and temperature, that could be even too, it could be too much. So most designers will not use 45 degrees phase margin. They in fact use higher, 60 degrees, maybe even 70 degrees. So what's the optimal phase margin, or what's the optimum location for your non-dominant pole? And to answer that question, we can look at the classical way of doing it. The classical way of answering that question is what? Take a control class. How do you analyze this problem? You analyze it in terms of damping, right? You say this is an equivalent second order system, and you know, if basically you define a Q factor. There's critically damped, there's underdamped, there's overdamped, and you can do it that way. That's fine. It's also pretty easy just to plot. Just, you know, it's such a simple function. Just plot the step response of your system as a function of the location of the second pole, and this is what we've done here. So this is the step function where k is a parameter, and k is basically the ratio of omega equivalent to omega t, right? And actually the other way around. So if, for instance, k is equal to a very large value, then that equivalent pole is gone, right? It's negligible. And so this is our settling time. Looks a lot like the settling time of a single pole system. So this curve, which is probably really hard to see, is the single pole system. And if let's say you have a factor of 100, that means that equivalent pole is just not in the picture, right? And the settling time is, again, almost exactly the same. And then if you go to the case of 1, that's 45-degree phase margin that we just looked at, you can see that it does overshoot by quite a bit, almost 20%, and then it settles down. And you know, you could play with this and see that, you know, 1 is probably too little, but if I make it a little bit larger, so here this is the case of 3. Interestingly enough, it almost looks like the case with 3 is settling faster, right? It's actually almost overshooting, but not quite, and reaching some tolerance. It looks like it's actually reaching a given tolerance spec faster than a single pole system. And so what you have to do is zoom in to this point. So this is a plot of the error, basically. It's 1 minus the actual step function, so this is the residual error, and again as a function of k. So here again is the case where there is no second pole and it decays simply exponentially. Case where second pole again is very far away from the unity gain frequency of interest. And then here is the case with 3 versus 1. 1, it reaches down to very good tolerance really fast, but then unfortunately it overshoots and overshoots. And so to wait to get to a given tolerance, you might have to wait 9 or 10 time constants before it's really small enough. Okay. Now, why can't we just stop here, right? Why can't we design a system that settles at, let's say, 2.3 time constants, and we have really good precision? What's wrong with that idea? Why wait 7 or 8 time constants to get really high precision? You can just stop. Make your system basically 45-degree phase margin, and then just design your system to stop after just about 2 and some time constants.
Yeah, I guess the time constant depends on like a lot of process issues, so it's not kind of fixed value.
Yeah, I mean, if you know, maybe that would be a good master's project, is to find a circuit that has a clock that varies with the time constant of your system, and then you could clock it so boom, over process and temperature, you're always stopping at this point, and you're getting yourself, you're saving yourself a few time constants. Well, it's probably not worthwhile, right? It's a pretty complicated circuit to even think about. Might as well just wait 5 or 6 time constants, and you're good to go. All right. Well, the interesting observation, though, is that this factor of 3 seems to be pretty close to optimal. And here's zoom in again for what's happening. This is the k equals 3 again. This is the normal. So this is a zoom in. This is 1% accuracy. This is 0.5% accuracy, and so on. You can see that, yeah, the k equals 3 does overshoot, but it overshoots so little that if you are trying to target, let's say, an accuracy level of about 0.5%, already at 3 time constants you're pretty safely there. And here's another plot. This is just a numerical plot of the settling time as a function of k, given that you want to hit some certain accuracy. And what's interesting here is that there seems to be a minimum. If you have about a k value of 3.3, you seem to have the optimum settling time. Okay, and that works out to, I guess, around 70 degrees or something like that. Okay, so there is the effect of the non-dominant pole. And for the most part, we can see that we can treat all the non-dominant poles and zeros as an effective non-dominant pole. What about doublets? So earlier in the class, we talked about circuits that naturally have basically a pole and a zero located almost on top of each other. And from what we've said so far, it seems like that's okay, right? If you have a pole and zero, they're almost right on top of each other. The overall transfer function, they cancel each other out, right? Well, remember, they're not exactly on top of each other. They're just slightly off. And so again, what we'd like to do is analyze the response. Let's say when this pole zero doublet is 1 plus epsilon, where epsilon is a small number. Let's say it's 1% or 0.1%. Okay? And so now the transfer function is, we have our zero, we have our pole, and we have our dominant pole. So we'd like to see how this pole zero could potentially impact our system. Okay? So just like before, what we do is we take the inverse transform with a step input function, and you do a partial fraction expansion. So we have a term that is actually settling with a time constant of this pole zero doublet, and a term which is the dominant pole time constant. If you solve this, do the algebra, a is equal to 1, b works out to, maybe somebody should check my math on this one. If you can calculate very quickly. Okay. Now I'm going to just, okay, let me just leave it. Let me make a simplifying assumption. Let's say that okay, I'll just leave it in that form. I'm sorry? This is epsilon. So epsilon here is defined as z over p. Okay. But thank you for checking. All right, so the output response looks something like this. We have our ideal step response. We have this is the dominant pole response that we've analyzed. And then we get some error term, which I've approximated here, but maybe I should double check this approximation. But the important point is that I have basically, this is my error term, and then this is my settling time of the error term. And so, you know, this is going to have some kind of magnitude. Let's say if P1 over Px, let's just take an example. P1 over Px, let's say, works out to be 10. And let's say epsilon is 1%. Then this is already 10%. So you can see that this term could introduce a 10% error in our settling time. And the time constant, just the way I picked it, worked out to be, you know, even though it's 10 times faster, actually no, I took the case where it's slower. So this time constant is then 10 times slower than this time constant. So clearly, the settling time is going to be determined by this pole zero doublet. So again, I think I screwed up the algebra, but the idea is that you're going to get a term proportional to epsilon and a term proportional to e to the minus t px, where px is the time constant of that pole zero doublet. And so your overall error, if you're not careful, could be determined by this term. Well, let's take another extreme. Let's say that this is an extremely fast pole zero, right? Let's say it's 10 times faster. Then this term again is very small, and this term settles 10 times faster. So it's not even there. So I guess we have a summary on the slides here. So switching to the slide here, we see that so this is just the equations that we just went through, and this is the final answer. And yeah, so the idea again is that this answer comes out slightly differently. Let's see what beta defined by. Okay, not important. This is just a constant. But the idea is that you do get the second pole due to the pole on zero. And so just like the fact that unless we had infinite precision, the pole zero didn't cancel out when we talked about them before, same story here. I have a pole, a zero, and another pole. I still feel the effects of that pole zero doublet because they don't cancel each other out perfectly. Okay. So here's a plot showing you the effect of the pole zero doublet. This is the slow time constant that we're waiting for. So this is the ideal step response in the red. The green is the step response with a doublet term, and then this is showing you how that doublet term is decaying to zero. So you can see that if I were really targeting high precision, you know, I might want to stop here if the pole zero weren't there, but this extra little term is forcing me to wait another 5 or 6 time constants. Okay. And so these are again the two cases that we have to be careful about. One is the good case where the pole zero doublet are much higher frequency, so we don't even worry about them. The second case is where the pole zero doublet are actually slower than our amplifier, and potentially they will set the settling time of our amplifier. Okay. Since we talked about poles and zeros before, I think we pretty much already talked about these issues. Any questions? Okay, so the next topic is slewing. Okay, and the idea in slewing is that I do my linear analysis, and my linear analysis says step response should look like that. I build my amplifier, and it settles like that, where this, instead of being exponential, is actually just a straight line. So my actual settling time has kind of, I can break it down into two regions. I can break it down into a slewing region, where it just goes at a constant rate, and then I have my, so this is a linear rate, and then I have my basically linear settling region. Kind of a bad term, right? Because this kind of looks linear. And linear settling gives me exponential. Okay. So in general, when I design amplifiers, unfortunately, I have to make sure that I take the slewing into account. Otherwise, I may completely underestimate the actual settling time of the amplifier. So what causes this slewing rate? Okay, anybody who did the optional homework have a nice way of explaining this? Yes, Christian.
You saturate the amplifier, so it just becomes a constant current source.
That's right. It's very simple. If I look at a simple model of an amplifier, let's say I have transconductance stage GM and a load capacitor. If I plot GM versus the input signal, then I know that I'm going to have, well, let me first plot the output current versus the input signal, I know I'm going to have a linear region where the output current is more or less proportional to the input voltage. Let's call this the input differential voltage. But if I make the input too large, right, this is not a perfectly linear amplifier. Eventually, it just saturates. So if I think about, let's say this were a simple differential pair, so this is IOD, and let's say this is ISS. If I apply a small signal here, then this IOD is about the GM of this stage times the input signal. But if I make this input voltage way too big, at some point, the maximum current I can deliver is more or less set by ISS, right? So for instance, let's say I swing this stage very low and this stage very high, right? So it's a differential input. That effectively turns off this stage, right? This stage then is fully on, and almost all the current ISS flows through here and flows into the output. So for a very large positive input voltage, I know I can't ever go higher than ISS on this graph. And because the system, is smooth, it's going to kind of saturate over to this side in some smooth way. And the same thing will happen on the other side, right? In the other direction, if I now do the opposite, this device turns off, almost all the current goes through here, gets mirrored to the output, and gives me a negative current. Okay? So my real amplifier has a characteristic that looks something like this. So if I now observe that the GM of my system is just the derivative of this curve, then it's going to basically look something like that. And let's call this V in max. So if the input is larger than some maximum value, this is minus V in max, because it's a symmetric system, then my GM kind of goes to hell. I have almost no GM, right? And really the small signal model of the circuit is not a very good model, because the small signal model of the circuit assumes that you have loop gain, right? You've got GM, that GM is in a feedback, I've got lots of loop gain, and so I've got this feedback amplifier that's driving the error term on the input to 0. Well, no, you don't have that, right? What you have is an amplifier that's dead, and its output is just being charged by a constant current. Okay? What happens if instead of having let's say I had a full op-amp. So instead of having just a GM stage, I also have a buffer stage, right, with some gain minus AV. Well, actually, let me complete this picture first. So let me stop. So let's come back to our simple stage. So in our transconductance amplifier, I have some load capacitance. I apply a big input differential voltage, and then my system just becomes a constant current ISS flowing into CL. This could be plus or minus, right, depending on the sign of the input. But if I put a constant current into a capacitor, I get a linear ramp, right? So dV dt, let's call this V out. So ISS has to equal to CL dV dt. In other words, the output has a constant slope of ISS over CL. So the output will just ramp. Okay. Now, because I have a feedback network, right, in place, as the output ramps, the input also ramps, right? And what happens is eventually the input gets small enough such that the amplifier turns on again. And when that happens, I go back into my linear settling. So at this point in time, my amplifier is on again. And of course, because we don't like dealing with nonlinear differential equations, we kind of make it piecewise linear. So we assume that the amplifier is off and then all of a sudden it's on. And there's going to be some smooth transition between on and off, but for simplicity we can just assume that if we've waited long enough, then after that wait, my amplifier turns on and I get linear settling. So this is the normal exponential settling. This is a linear circuit. Over here, I have a nonlinear circuit. And I have basically a ramp. Okay. Now that's all you need to know about slewing. It's actually very simple. You might say, well, what if you have a more sophisticated amplifier? Let's say you have an output stage. How does that change things? Okay. In fact, it doesn't change things much at all. If I have, again, if I apply a big step function right at the input, then I have a constant current, ISS, flowing out of this stage. This has very large input impedance, right? And so ISS effectively has to flow through this capacitor, and that produces a ramp voltage across this capacitor. And therefore my output will do the same thing. It'll ramp. So the question you're probably thinking about is, how big of an input voltage do I need to apply in order to observe this, right? And if you basically just plot I out over V in for your transconductor, you have the answer. So for instance, if it's a bipolar device, this curve looks like a hyperbolic tangent. And it turns out that if you're roughly 3 kT over Q, you hit this basically region where the current saturates. For a Mosfet, it's roughly square root of square root 2 times the overdrive voltage, or V star. So if your input is bigger than, let's say roughly, again, very roughly, because this comes from square law. But if your input is roughly larger than an overdrive voltage, right, a couple hundred millivolts, you will see slewing. And we do, unfortunately, you might say, well, why would you apply such a big signal to your amplifier, right? Aren't these analog applications and the input always small? Well, in these switch capacitor circuits, we do that every cycle. We apply a large input, right? So what I do is in cycle 1, right, remember I charge this up with V in, and I disconnect the amplifier, discharge this capacitor, and then in cycle 2, I present this circuit to my amplifier, which immediately causes a step, right? In cycle 2, I ground the input, and now I have a full V in across this capacitor, and this charge basically rushes over here and produces, get charge sharing between these capacitors, and I immediately get a step at my input. And we know that the first thing at the output of the amplifier, the step just travels through the output, so I get a step at the output, and then that causes this ramp to occur, and then finally, of course, we get into this linear settling region. Okay, so in fact, this is a very realistic scenario. It happens every cycle in a real amplifier. Okay, so step input is actually real. We really do care about the settling time for not a small, tiny little step, but a big step. Okay. In fact, it's kind of interesting that the settling time of a circuit in linear is independent of the size of the input, right? I can put a millivolt, and I have to wait 5 nanoseconds. I could put a million volts, still only have to wait 5 nanoseconds. Why is that? Very simple, right? Why is it that for a linear circuit, the settling time is independent of the amplitude?
It's exponential decay, right? So the rate that you approach the final value is proportional to your difference from the
Sure,
final value.
it's exponential, but physically what's going on? Why do we get an exponential? Where does the exponential come from? It's pretty much related to what we talked about, right? You want to take a guess? Dominant pole. That's not the answer to every question. Well, of course it's, but why do we get a dominant pole? I mean, he said it's exponential. You're saying it's dominant pole. You're saying the same thing. Yeah, it's exponential. But where does that exponential come from? All right, it's very simple. I don't know why you guys aren't giving me the answer. If I apply a million volts at the input, I get a current a million times, right, larger. So no matter if I make the input larger, there's more current available to charge that capacitor. The bigger the input, the more current is available. And so I get the same settling time. If I apply a millivolt, I don't need that much current. Whereas here, the system just can't provide enough current. It just runs out of steam at some point. So if I ask it for a milliamp, it says, okay, I have a milliamp. Ask it for 10 milliamps, it says, sorry, I just have a milliamp. So you're going to have to settle with a milliamp. And that's what you do. You settle with a milliamp, right? That's it. That's where the exponential comes from. The exponential comes from the fact that the current is proportional to the input. Once you break that proportionality, your simple first-order differential equation turns into, right, derivative equals constant, and you get ramping. Okay, if you look at some classic books, they always try to relate the ramping behavior to some small signal parameters. And it's kind of useful to do that because it gives us some insight on how we might improve the slewing in an amplifier. So here's a simple model. I have a fixed current, call it I1 for now. I'm going to be consistent with Gray and Meyer notation. And it's going through this integrating stage, and we know that the output will ramp proportional to I1 over C. In other words, we have this linear ramping. And I can write this as, well, also, so this is a large signal equation. Now, you guys know that the relationship between, let's call this delta Ix over delta Vx, some small input step, for very small input steps is just Gm by definition, right? So I could write delta Vx over delta Ix as 1 over Sc for small signals. That's because the second stage is really just an integrator. So in this derivation, you have to be careful to differentiate between small signal and large signal, right? So right now we're just talking about small signal behavior. Yes, I mean.
Isn't that delta VO over delta IE?
Yeah, thank you. So if I'm interested in how the output changes, and I have a differential current, right? That current integrates charge on this capacitor, and this is my transfer function. So this is small signal analysis. Okay. And so I could also write this as delta VO over delta IX is 1 over j omega c. And then I can write this as delta VO over delta V in is simply GM over j omega c. Okay. So everybody knows this equation. You use it in homework all the time. And what do we call GM over C, right? We call that the unity gain frequency. So at unity gain frequency, this term is equal to 1. And so what I can do is say that the second pole in my system is some factor k times unity gain frequency, right? Earlier we thought maybe k is equal to 3.3 is a good choice. Let's just take it equal to 1 for simplicity. That gives us a 45-degree phase margin. Okay. Again, this is just a simple calculation. That means that 1 over c is omega u over gm, which in this case is my non-dominant pole over gm. So when I write that the output for large signal, now back to large signal, I can just substitute for 1 over c as this expression, and I get a really interesting equation, which tells me that the slew rate, right, I want this to be as large as possible. This is that ramp rate, is related to I over GM. So if I want the ramp rate to be large, I want I over GM to be large. Omega 2 is kind of fixed, right? Because it has to be, let's say, 3 times the frequency of unity gain, right? So it's kind of a fixed number. Usually I'm designing an amplifier with a given frequency response that I want to achieve. And so the only way to improve this ramp is to make this ratio larger. Okay. Now earlier in this class, we looked at this ratio very carefully, right? And here we kind of have a funny result. It's not intuitive, right? At first, you think, what? I want to increase this? In other words, I want to decrease GM over I. Certainly we made a mistake, right? Because every other place, GM over I was a good thing, right? We wanted to maximize our GM. Now all of a sudden we want to minimize it. It seems like we've made a mistake. In fact, we have not made a mistake. A lower GM over I actually helps with slewing. And all we've done here, I mean, the reason that it's not a mistake is, let's say I take a bipolar amplifier, right? And I bipolar differential pair. I know a bipolar differential pair has a really nice GM over I, right? Because of that exponential. Now let's say I do something terrible and put series feedback here, right? Then my GM drops, right? So now my GM drops by the loop gain of the series feedback. And so I've decreased my GM. So relative to I, you could see that GM over I is now lower. It's lower exactly by the loop gain. What does that look like here? Well, if I plot the equations, it looks something like this. I've actually expanded my input range. Remember, when this is straight line, that's the range over which the circuit can respond exponentially. So all I've done was I've basically given up some gain, and in return, I've gained a higher input range, right? And so now, over this whole input range, my amplifier will respond exponentially. So let's say before, this was, what did we say, a few kT over Q. Let's say this was 100 millivolts. And now I've increased this, let's say, to 500 millivolts. Just say. That means that before, if a step was bigger than 100 millivolts, it would ramp. Now I can tolerate a step even as large as 500 millivolts, and it still will not ramp. Okay. So let's just compare. So the slew rate with no feedback is 1 over C. It's basically I over GM times omega 2. And for a bipolar transistor, the current is half the current, the total current. Let's call this ISS. So I get 2 kT over Q times omega 2. It's a fixed number. Slew rate just depends on the location of the non-dominant pole, right? Now if I substitute this equation, slew rate with RE is basically ISS over GM omega 2, and it works out to be a factor of 1 plus the loop gain larger. That's great, right? My loop gain is 10. I've got 10 times more input range. What's the limit? How much larger can I make it? Can I make this 1,000? 1,000,000? Yeah. Michael?
It probably depends on the gain you need for the amplifier.
Yeah, it's going to kill my gain, right? But let's say that I've got a nice nested Miller compensated amplifier stage following, and I have no limitation. I can put as much gain as I want. What's another limitation?
ICRE. The ICRE has the limits on the voltage supplies.
Really? Why can't I do something like this? So your argument is that there's a voltage drop, just an IR, right? ISS over 2 times RE, right? And this eats up headroom, right? Can I just use 2 current sources? Would that work? There's no current through this guy, right? Can anyone think of a disadvantage of this versus this? So here, headroom is definitely an issue. But this is perfectly legitimate, right? But I'm going to claim that this is better, always. Why is that?
Because of the common mode?
Common mode? No, for the common mode, it's still going to be the rejection of this current source, right? If I apply a common mode signal. Right, for a common mode signal, this resistor doesn't exist, right? And so you just see an RE equal to the output resistance of that current source. Well, you could argue that matching is going to be an issue, right? Because now these current sources have a mismatch, and so I get more common mode, differential to common mode conversion. Okay. What else? I'll give you guys a hint. What if on the test I asked you to calculate the noise of this guy versus this guy? Which do you think has less noise? And why? Why being the key question. All right. No guesses? 5% of your grade. Well, what are the noise sources? Think about the different noise sources that you have in the circuit, right? In this circuit, does this current source contribute noise? Depends. If output's differential, no, because it's common mode signal, right? Because I inject the same noise into both sides, and so I subtract it out. Here, these are two different current sources, so even if I take a differential output, the noise sources are uncorrelated. So then I see the noise of the current source. Okay. So this one has higher noise. So this one is basically correlated noise. Which is roughly 0 for differential output. All right, well, what about a Mosfet? Well, one of the advantages of a Mosfet is actually it naturally has a higher slew rate because it naturally is a dog when it comes to GM, right? Naturally, the GM is much lower for a given current. So if I substitute here for GM, GM goes like square root of current, and so I get an equation that looks like this. These are all kind of constants, and then this is a term that goes like current. So you can see that to improve the slew rate, you just basically, if let's say the currents are fixed by other considerations like settling time, to decrease the slew rate, to increase the slew rate, you decrease W over L. Okay? But if you do that, then your GM will drop, right? And in order to have the same settling time, you also must drop CL. So really the only way to improve the slew rate is improving the current. And because it's a square root, you don't get quite the same improvement of slew rate that you would expect. I'll let you guys, because we have limited time here, think about this at home. Basically, let's say I fix my design parameters. I want to meet a certain gain, certain settling time. How can I improve my slew rate? It turns out you can by scaling I, but you have to think about it because you can't just change I without changing everything else, right? Okay, if you want to see a good example of a slew rate calculation, I'll post the homework solutions, if I remember, before lunch today, so you can look at that. Don't worry, it won't be on the midterm. Basically, the topics that we covered up until, let's say, last lecture are fair game for the midterm, but you don't have to, today's lecture, the first half was hopefully a review, but the second half on the slewing and stuff like that, we don't have to cover. Okay, we still have a minute left. I just want to talk a little bit more about amplifier design. So usually when we're designing an amplifier, we have a couple of important overriding considerations. One is the speed, right, which is really the settling time, and the other one is resolution, which is epsilon. So we want to settle within a certain time, within a certain accuracy. Okay? And we've learned in this lecture and last lecture that there's two components. One is the static settling, which is really governed by how much DC gain you have. At the end of the day, it's kind of surprising, but that DC gain matters. Because as your amplifier settles, as you wait long enough, it's really that DC gain which is rejecting your error signal. So usually we have to budget this error into two terms, right? A static term and a dynamic term. The dynamic term also, we found out today, has two components. It has linear settling time and it has a nonlinear settling time, right? And the idea is that we know from our calculations that settling time is just directly proportional to current. If I want to settle faster, I just have to burn more current. The nonlinear settling time, on the other hand, is a function of GM of the device, right? And if you fix your V star, then it just becomes also a function of current. So at some point, in order to improve the settling time, also in the nonlinear region, you have to, again, change the current. So at the end of the day, it's the larger of these two that determines the power consumption that you need in a circuit. Okay, stop there. Don't forget to turn in your homework.